Okay, for this chapter, it's chapter 11, we are going to be graphing trig functions. So, if I were you, I would maybe take and pause the video right now, and on your first page of notes here in chapter 11, you can see I've added in blue different angle measures along the x-axis and then also around the unit circle. So maybe pause the video and put those in if you don't know those angle measures, because those angle measures are what we're going to use to show you how to graph y equals sine x. Okay, so welcome back if you paused. So what we're going to be looking at is, on the unit circle, the y-coordinate represents the sine of the angle. So on the unit circle we have our quadrants, and they go around as quadrant 1, 2, and then 3, and quadrant 4 is over here. So what we're going to do is take that and put it on a linear graph, reading it kind of from left to right. So we're going to transfer now so that this is quadrant 1, this is quadrant 2. Let me move this out of the way. (90 to 180). 180 to 270 is quadrant 3. And then 270 to 360 is now quadrant 4. So I'm kind of like taking this unit circle and unraveling it and writing it out linearly. So to show you how this works, I'm going to use the lengths of the y-coordinates. So if you look at the sine of 30 degrees, well, first of all, the sine of 0 is the y-coordinate of 0. So we'll just mark that, I guess, in green here. So the sine of 0 is right here, marked in green, at the origin. Now the sine of 30 is represented by a distance from the x-axis up to that coordinate, radical 3 over 2, comma 1/2. These are accurate measurements. So this angle here is truly 30 degrees. So these are actual correct angle measurements. So that distance there would represent the sine of 30. So I have it over here, which yours are on the axes. So the sine of 30, I'm going to take and put it at the 30-degree mark. Okay? And then for 45, it's in dotted red line, and that's this size over here. So the sine of 45 is represented with that length. And now look at our radius, is 1 to this point right here. Our radius is 1 right to this point right here. So these lengths should make sense. Okay, now the sine of 60 degrees would be represented by radical 3 over 2. So if we had a radius of 1, radical 3 over 2 is as a decimal, like around 0.866. So if our unit of 1 is the length of the radius, say from here up, there's our unit of 1, this should represent, the sine of 60 should be about 0.866. So our unit of 1 for the sine of 30 is going to be half that. 0.7 is approximately equal to radical 2 over 2. So the red is about a length of 0.77, and then my sine of 90 is going to be that length of 1. So that's, I'm going to just draw that in. Let's use yellow. So my length of 90 is going to go up to 1. So all of these distances are representing those angles. Now, when I get into quadrant 2, I could take and move this piece over here. Okay, so if I move that piece over there, it's going to hit about the 120 height. So let's hope I want to clone this, and then I want to move it over to 120 over here. So I'm just getting the heights. Now I want to take the red one now. There we go. And I want to get the height at 135 degrees. So I'm going to clone that. And then I'm going to put that at 135 degrees. So that distance is about 0.7. And then I'm going to take this distance here. And notice it's the same y-coordinate as in quadrant 1 at 30 degrees. So 150 had that reference angle of 30. So now I'm going to clone that and take that distance over here at 150. Okay, and at 180, look at the y-coordinate, it's 0. So I'm going to just mark that in green here. 0, 180 are both 0. And what we're going to get here is a sine curve graph. Now I'm going to keep going with this, going back and using this, grabbing this blue, that blue distance to represent the 30 degrees. No, this was the 60. So I'm looking for 210, so actually I need the green one. So if we put this here, see, it's the same. So all I'm doing is getting all those distances. But I'm going to put it down here at 210 because we went negative. So now I'm going to go below the x-axis. So notice the difference here. And then I'm going to take the 45-degree reference angle. Okay, and put that here, and we'll clone that one, and put that at 225, and then we'll move this one down to 240, clone that one, and put that at 240. And at 270, look at the y-coordinate, it's -1. So I'm going to go down here with yellow. I had to look at the color I used to -1. All right, and then we'll just continue the same thing for 270. We did that one. Now for 300, that should represent a blue distance. So clone it there and draw that in at 300. And then at 315, we're about there. So we'll clone that and put that piece in at 315, and the last one is at 330. All with these reference angles of the same amount, 30, 45, or 60. Those distances are the same. But now notice we're down, so that's why these are down below. And then at 360, the y-coordinate is 0. So going to put another point there. So notice 0, 180, 360, all at 0. 90 was at 1 and 270 negative. So now what we're going to do is connect this. And I want to do just like this. So this is a rough estimate. I'm doing a rough sketch of what a sine curve looks like. So there it is. All right, go to the next page. And we're going to do the same thing with cosine. Okay, so if you need to pause and put those values in again, go ahead and do that. So sine's a little bit easier to do just because they're the y-coordinates and they're already going vertically. Now I'm looking at the x-coordinates. So I have, for 30 degrees, I have a green segment. For 45, I have a dotted red segment. And for 60, I have a blue arrow. So I'm representing the x-coordinates this time, which is why I place them going horizontally. So you have to imagine taking this horizontally and then flipping it vertically. So the green segment is the same as the one over here just floating around on the graph. The same length. I just rotated it. Okay. So take a look at the cosine of 0 or 360, which is 1. So now I want to get at 0, I'm up here to 1. So it's not going to be the same as the sine. And remember, the quadrants are going 1, 2, 3, 4 around on the unit circle here. But then they change when you're coming over here and graphing to 1, 2, 3, and 4, so that we can represent this linearly. All right, so then we're going to do 30 degrees. The cosine of 30 degrees, if you look at that x-coordinate, is radical 3 over 2, which should be your length of about 0.866 compared to your length of 1 for your radius. So if I take and just rotate it, it would be represented by this green segment. So I'm going to drag that over to 30. For 45, it's the red segment, which I have right here. And the blue one is going to represent the cosine of 60. So it's going to be half the distance of a radius of 1. All right, so now at 90, look at your your x-coordinate. It is 0. So I'm going to mark that one with that big green dot. And then I'm just going to use these segments again. So for 120 degrees, I'm looking at the x-coordinate. It's -1/2, so that'd be this distance. Okay, so it'd be that little -1/2 right there. So I'm going to clone that. And then basically what I'm going to do is I'm going to rotate that. I'm going to do this once, and then I'm just going to make clones of these so you can see. So I'm going to rotate it down and then bring it down to 120. So it should be about halfway. If it's not, that's my fault there a little bit. All right, then take the one at 45, which is the red dotted one, and I'm looking at the x-coordinate, so I'm putting that up there, that distance. And if I clone that, and I bring it over here, I need to rotate it and put it at 135. Sometimes this chart is also written just a little differently, and that should be about 0.7. And then this green segment is representing that x-coordinate here of -radical 3 over 2, which is about -0.866 if we would actually plot that. So I'm going to clone that, bring that over, and rotate that down. And that should be at about 0.866. Alright, so there we go. So we're starting to get another graph, and we can just continue the same thing. So now for 210, that's going to be this green segment again, right about there. So it's going to be one of these green segments, so I'm just going to clone it here and put it there. Oh, I forgot 180. 180, the x-coordinate's -1. So let's get a yellow again, and now we're going down to -1. For 225, that distance would be represented by the red dotted line. That distance, we're looking at the x-coordinate as if we were plotting it off that x-axis. So I'm going to just clone one of these. It's the same distance. And put it at 225. And then this last x-coordinate of -1/2 for 30 degrees. We'll just clone one of those. And bring that to 240. At 270, look at the x-coordinate. It is 0. So big fat green circle there. And then you can hopefully see the way this is going to go. For 300, it's going to be this one of these little blue arrows. So again, I'm just going to clone that one. And then here we are at for 45, or the x-coordinate radical 2/2, so it's one of the red dotted ones. Now notice how I'm back up when I'm back up into I'm back up above the x-axis. Now why was I down here? Because the x-coordinates were negative. When you plot those x-coordinates in 2 and 3, they're negative. When you plot x-coordinates in 1 and 4 quadrants, they're positive. Okay, and the last one, so we'll just clone one of these. And then at 360, we're back to 1. So now if we take and we connect this, it looks like that. And that's y equals cosine x. Okay, so that's how you kind of take the unit circle, kind of unravel it. You're looking at the distances of the x-coordinates for cosine, and you're looking at the distances for the y-coordinates for sine, and how they relate to that radius of 1. Okay, so you could take any length radius of 1. I had to make mine decent enough so that I'd get decent segments to draw. All right, let's now turn and let's do the graph of y equals sine x on the calculator. Okay, here we go. So take your calculator and put it in degree mode. Alright, and then go into y1 and clear that out, and let's put sine x. Okay, so to graph this, let's set the window. So hit window. Show you a couple of ways. You can go zoom, trig, zoom 7. And what that will do is kind of set it up in a window that's going to go from about negative 360 degrees to positive 360 degrees. But if you hit window, we're going to just graph from 0, so make the x min 0 to 360, make the x max 360. You see here currently the x max is 352, but we'd want to go to 360. The x scale I usually go by 30s, which are the little marks on the x-axis. You don't want them to go by ones anymore because there's 360 of them. And then the y-min you want to have just keep at -4 and the y-max at +4. And then hit graph and you'll see a picture in just quadrant. You'll just see it, it's quadrants 1, 2, 3, and 4, but you'll only see one sine curve. You will see the sine curve like we just drew when we took the lengths of the y-coordinates. All right, so if you go to second window and you wanted to look in your table at values to plot some points, you would want to go here and have the table start at 0 and then triangle TBL increment by 30s. So then hit second graph and you can now see how your table will go by 30s. You don't want it going by ones or you'll never get to 360. Okay, so let's go back and plot some points here then. So the x-min was 0, the x-max was 360, the x-scale was 30, the y-min -4, and y-max +4. So let's take and draw our axes. Now, I cannot get the axes to I can't use a ruler real well on the smartboard, so I'm doing my best to make this as straight as possible. So each little mark can be 30 degrees, okay? So 30, 60, 90. So I'm just for like the first one, I'm going to say that's 30, 60, 90. And then, so we want to, you know, do this in degrees, but yet we're going to kind of pretend we're in radians, so we're going to put pi over 2. So pi over 2 is 90 degrees. And then the next marks would be 120, and I'm just going by 30s, so 120, 150, and then 180. So this sixth mark is pi. And then we're going to go 210, 240, and 270. So the ninth mark is 3 pi over 2. And then 300, 330, and 360. So I skipped the 45, and that's okay. We usually go by 30s. So that's the x-axis, the way you want to mark it. Now remember we went from -4 to 4, so I usually go up 2 blocks and do 1, and down 2 blocks and do -1. Otherwise, it's too close if you count each block as 1. And then I plot my points. So if we looked at our table of values, at 0, it was 0. At 30, it was 0.5. Okay, so if I just go back there, and at 60, it's 0.866. We mentioned those values when we were grabbing the segments. And 90, it's 1, 120, 0.866, 150, 0.5, 180, 0. So at 60, I'm at 0.866. And at 90, I'm at 1. Back down, 0.866, 0.5, 0. If I go back there and I arrow down through my table to see what's going on to 360, I'm then going in the negatives, -0.5, -0.8. So it's a repetitive pattern. So I'm at -0.5, -0.866, -1, -0.866, -0.5, back to 0. And then I connect it. So there's y equals sine x, and that's the graph that we had on the previous page. What you are looking at is one cycle. one cycle of the sine function. The sine function is not just the top half of the curve. The sine function is completely that. That is one graph of y equals sine x. If you graph y equals sine x from negative 2 pi or negative 360 to positive 360, you should see, let's take and go to window and make that negative 360 and hit graph. You should see how many cycles? 2. So y equals sine x is called a periodic function because the graph repeats every 2 pi or 360. So the period of pi of y equals sine x is 2 pi or 360. So a couple of questions. Is the graph of y equals sine x symmetric with respect to a reflection in the origin? So if you take your notes and you flip them upside down, do you get the same graph? Because the reflection of the origin is that rotation of 180. So if you just flip it around, you get the same exact graph. Okay, so we reflected at 180 degrees and it was the same. Is the graph symmetric with respect to the translation t negative 2 pi comma 0? So if you took and you look at this and you slid it over 360 degrees to the left. So if you took like each point here and you slid it over, it should fall on top of the other graph. So yes, and if you don't understand that, ask your teacher to help to point that out to you. What's the maximum value of y on the graph of y equals sine x? Well, if we look there, or if we look at our graph, our maximum value looks like it's 1. What's the minimum value? The minimum value is negative 1 if you look at the graph. What's the period? Well, we just said the period is 2 pi. Is the sine function 1 to 1? No, it does not pass the horizontal line test. What's the domain of the sine function? Well, the domain, this could just keep going on and on and on. Okay, so this cycle is just going to keep going on and on and on. So it's all reals. It just keeps going on and on and on. What is the range? Well, if you look at the y-coordinates, though, they only are going to go from negative 1 to 1. I dipped this accidentally a little below and above that. But it should vary from negative 1 to 1. So back to those translations a little bit. So just imagine sliding this green graph that I just made 360. It would fall right on top of the red dotted. Or if I moved it to the left, it would fall on top of that if you just slid this green line. Okay, so there's your first lesson for graphing sine. You'll do cosine in class. Have a good night.